All right, so we're going to take a look at the assignment that this is related to. The topics really kind of flow together here over the next few sections. But what I'm going to do is I'm only going to cover the part today related to the next assignment. That's how I'll kind of break this up. Just because I don't want to I know you guys are super smart, but I don't want to overload you each day with new stuff. I want to give you a chance to kind of digest this, and we'll come back on Wednesday and we'll push this a small step forward. This will be the stuff for the practice 2 from 5.7. Practice 1 is the synthetic division. Actually, just polynomial division, both long division and synthetic division. And what we're going to specifically take a look at today are the remainder and factor theorems. By themselves, they don't seem like much, but the applications are interesting. So let's start off by looking at a couple. Before we look at, we're going to do this, as you might anticipate. We're going to look at some quotients of polynomials. Okay, so we're going to simplify some quotients of polynomials. But before we do that, you've probably noticed that a lot of times I like to start off by looking at numbers. And then we'll kind of just so we can get an easier representation of the concepts that we're going to look at with the variables, right? And it oftentimes works that way. This is a good thing to do in math. Oftentimes you can kind of think about what this would be like with just simplifying an expression with numbers and then extrapolate that into variables, and it helps you remember what the relationships are like. Okay, so what about 25 fourths? What is 25 fourths equal to as a mixed number? 6 1/4, right? Okay. So 6 1/4 really means we'd write it as 6 and then a 1/4 next to it back in the day when we used mixed numbers back in middle school. We don't do that anymore. But what we meant by that, by 6 1/4, was actually 6 plus 1/4, right? And how do we get that? Well, we would get that by using division, and 1 would have been our remainder, wouldn't it? Right? What if we were to clear the fractions by multiplying a 4 through both sides? Well, then we just write that as 25 equals 4 times 6 plus 1. Everybody see that? Okay, so is 4 a factor of 25? No, it's not. And how do we know? I guess I should have had this covered up. I should have just slid this down. Does it make sense that we know that that 4 is not a factor of 25 because we had a remainder, right? When you guys did that math in your head and you said 6 and 1/4, you had to think, okay, 4 goes into 25 6 times evenly with how much, there was some left over, right? So it wasn't a factor. Whereas 32 over 4 is just plain old 8, isn't it? Right? Or if we wanted to write it with a remainder, which would be kind of silly, we'd write it like that. 8 plus 0 over 4. 0 remainder. Okay? So then 32, if we want to write this, if I multiply through by 4 to clear the fractions in both cases, just look like that. 4 times 8 or 4 times 8 plus 0, right? Is 4 a factor of 32? It is, and we know it is because in this case, r does equal 0. The remainder is 0. So what are we emphasizing there? What's probably the important point that we just outlined there? Say it again. In order for the denominator to be a factor, right? Perfect. Okay, so we associate the denominator being a factor of the numerator when the remainder is 0. You already knew all that stuff, but here's just a visual representation. So now let's carry that forward and let's look at it in terms of some examples which have variables in them. So we want to know, is x minus 2 a factor of 2x squared plus 3x minus 12? Well, I mean, how would we find out? How would we answer that question? By dividing, right? Doesn't that make sense? We would just divide it and see if the remainder was 0, right? And this is one where we can easily use synthetic division. It's really quick and easy to do. Why are we able to use synthetic division here? instead of having to use long division? What's the criterion there? We can always use long division, right? But long division was a little painful, right? It looks uglier on the board. There's more to write. When are we able to use synthetic division? I want to know how you're feeling about that concept. Give me thumbs up if I'm pretty sure I know the answer, thumbs down if I have no idea, thumbs sideways if you're just kind of unsure. Okay, all right, okay. So we don't know thumbs up. That's all right. That's what I want to see where we are on that. Remember that last time when we were talking about synthetic division, we said the only criterion for synthetic division is that the bottom has to be linear, right? Can't be quadratic or higher. The denominator has to be a linear polynomial, so the biggest power of x is 1, and it has to be written in the form x minus k, where k is just some number. K could be a fraction, right? But it has to be in the form x minus k. Does that make sense? Let me go back. I want to point out being able to see there's some research that indicates that if you can re-immerse yourself in the original learning environment, you're able to retain and access prior learning more easily. So let me go back to that. I want to go back to that real quick here. Here's our synthetic division stuff that we did. Right here. This page. Okay, we called it A at the time, right? When the denominator is linear and can be written in the form x plus or minus some number. We could just call that x minus k now. After today, we'll call it x minus k. Okay, then we can use synthetic division. Okay, and we even looked at an example, remember, where the bottom, we had to rewrite the bottom. Remember this one? Where we had to divide both the top and the bottom of this one by 2 so we could put it in the form x plus 5/2 so we could do synthetic division. Remember that one? If not, you might want to just take a look. This was kind of at the end, towards the end of our synthetic division talk we had, so you might even want to just take a quick peek at that one on video. The videos are all up on the YouTube playlist. You're going to get one like that you had one like that on the synthetic division assignment, I'm pretty sure, and you're going to get another one like that on this assignment. That's kind of a higher level thing, but you guys get to do higher level stuff in here. You're so smart. So back to business here then. If we want to determine if x minus 2 is a factor of this polynomial, we'll just divide it in there synthetically. And we're just looking to see what we get in the remainder box, right? If the remainder is a 0, yes. If not, no, okay? All right, we want to see if we can make another connection here. I'm going to ask you something else here. There's another really cool connection that you're going to be surprised by, and this is a fun one. So what if we evaluate this function at 2? And 2 is significant because 2 is the 0 of the factor in the denominator, right? That's why the 2 is out front, remember, because the number that goes out in front of the synthetic bracket is the 0 of the denominator, right? So if we evaluate this function at 2, let's see what we get. 2 times, we can just kind of keep track here. How about 2 times 2 squared, that's 8, right? Plus 6 is 14, minus 12. Would you agree that's 2? Okay. All right, I want to see if you guys can just kind of, you don't have to say anything out loud yet. You can sort of test drive this. We'll look at another example where you can check this. But are you seeing any connections here? When we evaluate the polynomial in the numerator at the 0 of the denominator, we got 2 as an output. And here's a graph of it. Okay? The input value was 2 for our function, right? We evaluated p of 2, and the output value was 2. Okay, let's try another one. How about this one? So how are we going to determine if x minus 1 is a factor of that yellow polynomial? What are we going to do, everybody? Divide it, and we'll use synthetic division, right? Because it's easy. Okay, so you guys just check this. Give me a thumbs up if you agree with my synthetic division there. Thumbs down if I made a mistake. Okay. Thumbs up if you agree. Thumbs down if you don't. Should we quickly review the synthetic process? Would that be a good thing to do? Okay, let's do that. So let's just walk through how we get this. So when I'm trying to divide this synthetically, we put the 0 of the denominator goes out front. The coefficients of the numerator are what we write across the top row. And remember that if there were a missing power of x, I'd have to have a 0 coefficient there, right? So we're starting with the first column represents the coefficients of x cubed, coefficients of x squared, coefficients of x, and the constant. Our remainder box always gets lined up underneath the constant, underneath the bracket. And then the process we follow, we drop the 2 down. Whenever a number appears below, we multiply by the outside number. So 2 times 1 is 2. And we add synthetically. We do the opposite of long division. We add the rows synthetically. 5 plus 2 is 7. 7 times 1 is 7. Plus negative 11 is negative 4. Times 1 is negative 4. Add those up and we get negative 18. Okay? So there's our, so it looks like that's correct. So there's our synthetic process. So then doesn't that tell us that, that our result is going to be, this is going to be the constant. This is the remainder, right? So that's the constant, coefficient of x squared, coefficient of x cubed, coefficient of etc. If there were more numbers. So it looks like we top out at x squared. So we get a 2x squared plus 7x minus 4 plus negative 18 divided by x minus 1. That's what remains over our denominator. Okay, there's our simplified version. Okay. All right, so what if we evaluate this function at 1? Well, that's pretty easy to evaluate at 1, isn't it? If I evaluate this thing at 1, I just get 2 plus 5 minus 11 minus 14 is negative 18. Are you seeing a pattern here? What's the pattern? Yeah, how about that? That's pretty interesting, isn't it? Whatever the remainder is, when we divide using long division or synthetic division, when we divide by x minus k, we divide by a linear denominator, the remainder is always equal to the value of the function at 1 in this case, right, at k, whatever the value of the 0 of the denominator was. If we evaluate the polynomial there, we always get the result that's already in the remainder box, right? And if we look at a graph of this, well, there it is, right? This is the point. When we evaluated this at 1, we got negative 18. And so on the graph, we'd be over 1 and down 18, right? Okay, this is pretty cool. This tells us that synthetic division is really a 2-for-1 deal. Not only is it an easy way to do the polynomial division, the output of the remainder box is a way of evaluating the function at k, right? That's pretty cool. It's a simple way to do that, okay? And it leads us to the polynomial remainder theorem. What this tells us is that if the polynomial f of x is divided by x minus k, so k is the 0 of the denominator, right? Then the remainder is the value f of k. How about that? Right? So as a shortcut way of getting to f of k, we can just find the remainder synthetically. And then it ends up being, you can call it synthetic substitution, or I prefer synthetic evaluation. Either way, you can use it just to evaluate a polynomial. Okay, let's prove that though. We don't do a ton of proof in high school algebra classes, but for you guys especially, I want to walk you through a couple proofs, just so you don't lose sight of this is an important part of math. How could we prove this? How can we prove the polynomial remainder theorem? So we're going to prove this statement. If a polynomial f of x is divided by x minus k, then f of k equals the remainder. That's what we want to prove. Okay? So here's a way we could do that, right? We'll just start off by setting up our quotient. Okay, so we've got some polynomial we're going to call p of x. Could be anything. Polynomial is p of x divided by x minus k. Would you guys all agree, and I want you to give me thumbs up, thumbs down, thumbs sideways on this. Would you agree, and are you comfortable with the idea that the result we're going to get is going to be some polynomial part of the answer, which we'll just call q of x? We don't know what it's going to be. In our last example, it was that, right? We got that polynomial answer plus, plus some remainder that we'll call r divided by x minus k. Okay, we good with that? That it's going to take that form. We don't know the specifics, but that's the form it's going to take. Okay? All right, so if we want to clear the fractions, I could distribute an x minus k through both sides. And that's just going to cancel the x minus k's on the left, right? So those guys will cancel. Over here, if I distribute it, I'm going to get x minus k times q of x, which is just the polynomial part of my answer. Plus, over here, the x minus k's will cancel. So we just get that, agreed? So far, give me thumbs up, thumbs down, thumbs sideways. How are we doing on that? Okay? Okay? All right, so now the next thing is, let's evaluate this at k, because k is the zero of the denominator, right? So if I evaluate this thing at k, I'm substituting all my x's become k's, I'm going to get k minus k times q of k plus r. We don't know what q of k is, because we don't know what q of x is, but we sure as heck know what k minus k is. That's 0, right? So 0 times q of k is 0, and so our answer, we just proved it. Pretty cool. We just proved that p of k is always equal to r. And does everybody see here that this is a completely general proof? We weren't specific at all. We didn't say anything about what the original polynomial was, or what we're dividing by, or what q of x was. It's going to work in all cases. That's always true, right? So there's our proof of the polynomial remainder theorem. Okay, let's use it. Okay, I want to do one more thing before we use it. Let's use it real quick. Okay, how am I going to do this problem? The old-fashioned way, I'm going to call it for now, is the way we would have done this last week. You know, before today, if I told you to evaluate this function at -1, you know how to do that. You just plug it in for x, don't you? Right? Now, in this case, that's pretty easy to do because the number we're plugging in is -1. -1 to any power is easy to calculate, right? But you can imagine that if that weren't -1, what if it were -17? Then it would be harder without a calculator. It would be harder to plug those values in there and calculate these enormous exponents, right? -17 to the 5th, what's that? That's going to take you, without a calculator, that's going to take you a little bit to compute, isn't it? You see my point? I'm sorry, I'm expecting an important call. I am, hang on here. Oh, that's not it. Okay, I can delete that. Oh, never mind. So we would get some pretty big exponents there. If you think about computations that you do about arithmetic operations, we're going to talk a lot about this in calculus class in a couple of years, about some tricks that we have for reducing the complexity of arithmetic calculations. So our arithmetic operations, the easiest ones are addition and subtraction, right? One step up the ladder would be multiplication and division. One step up the ladder would be exponentiations. What's that starting to look like, by the way? That looks an awful lot like our order of operations tree, doesn't it? Right? So they get more complex as you move up the ladder. It's harder to do these computations. So if we want to work as far down that ladder as we can, right? Well, if we're going to evaluate a polynomial old school style, we're going to have to use exponentiation because we're taking powers, aren't we? Okay, but think about what this looks like using synthetic evaluation, right? If I'm going to do this using synthetic evaluation, this is pretty easy, right? The value that I'm plugging in is what goes out front, right? And then I'm just going to put the coefficients of the polynomial up top. So what are those in order, everybody? Negative, whoops, hang on here, so negative 1, what's next? Negative 1, what's next? Oh, no, 0, how come? Because there's no x cubed term. So we have to have a 0 x cubed, 0. Good. And that's what we're looking for, right? The remainder is the value of the function at negative 1. So then we just have to crank through the synthetic division, really, but we don't care about the division part. We just want the remainder this time. So negative 1, what goes there? You guys tell me what goes there. That's it, right? Okay, now I know this one would have been pretty easy to do the other way, but if this had been something like a negative 17, this process would have gotten slightly harder because we'd be doing some multiplying of some slightly bigger numbers. Adding and subtracting is always easy, right? But it's a heck of a lot easier than having to do that exponentiation, isn't it? So this is an improvement. This is like a fringe benefit of synthetic division, is we get this extra little evaluation trick that we can use, okay? So that's what we get. So what's that tell you about f of x? Is x plus 1 a factor of f of x? Hold that thought. We'll come back to that one. Come back to that. Okay, so let's scoot back here then. Let's go back to this example. What I was going to do. We've done 2. I want to do one more. So we're going to determine, is x plus 1 a factor of the yellow polynomial? Okay, so you guys check my synthetic division, please. Give me thumbs up when you can agree. Everybody take a look. I'm waiting for a thumbs up from everybody on this. Or if I make a mistake, let me know. Does that all look good in the synthetic brackets there? Adelaide, do you agree? Okay, looks good. Yeah, I think it's right. Okay, so then that's telling us that the remainder is 0, isn't it? Right? Agreed? So in other words, the yellow polynomial divided by the blue polynomial is equal to the green polynomial, right? Is x plus 1 a factor of the yellow polynomial then? It is, right? Because what we said at the very beginning, because the remainder is 0, it is a factor. Okay, well, what did the synthetic evaluation yield? I mean, we could check it old school by plugging negative 1 in, but we're getting 0, right? That's an important connection. So what do we know then? How can we always tell if x plus 1 is a factor? If we get no remainder, right? Okay. What does that mean though? look what happened here. When I evaluate the function, I get 0 back. And so if I look at a graph of this, what do you notice here that's different? This time when I evaluate the function at the 0 of the denominator, which is -1, I got 0 for the answer, right? It's an x-intercept. Those other graphs were not, right? If we go back and look at those other graphs, I had remainders, and the remainders were given to us by the remainder box. Those are the values of the function. Well, they weren't x-intercepts because the value of the function at 1 in this case was -18, not an x-intercept. It wasn't equal to 0. And here it was +2. It wasn't a 0, right? So this is just putting, you guys, all these pieces you already knew, but we're just rearranging them in a slightly different way that's giving us another strategy, right? Isn't this just telling us that if k is a 0 of f of x, and how do we know that? We know that if the remainder is 0, right? Then that can only happen if x minus k is a factor of f of x. Everybody see that? I'm going to backtrack for 1 second here. Let's go back to this picture, right? Look at all the zeros that pop up. My remainder is 0. The value of the function at -1 is 0, okay? So we already can see that x minus k is a factor of, we called this p of x, was the yellow one. Then r must equal 0. We said that at the beginning. Okay, well, recall that the zeros of a function, what does it mean to be a 0? The zeros are the places where the function is 0, right? Where the value of the function is 0. So we want the values of x that make the output of the function 0, right? Okay, so then k is a 0 of f of x if and only if f of k is equal to 0, because we want the output of the function to equal 0, right? And so that leads us to, that leads us down towards this factor theorem. We've seen that dividing by a factor always produces a remainder of 0. So therefore, we get this elegant little factor theorem. That's it. If k is a 0 of f of x, then x minus k is a factor of f of x. And if and only if means it goes both ways. It's a biconditional statement. So I could start here and say if x minus k is a factor of f of x, then k is a 0, or flip it around and go the other way. They each lead to the other. They're necessary conditions for both of those statements. They both have to be true at the same time, or they're both false at the same time. Okay? All right, so how are we doing? Thumbs up, thumbs down, thumbs sideways. Where are we here? Okay, it's a lot of stuff I'm throwing at you, but let's look at some examples that illustrate this. Okay, so first of all, I want to show you that this is really not that profound. You guys already knew this without even being aware of it. Let's go back and look at a problem that we probably did a month and a half ago or more. If I said find all the zeros of this function a month and a half ago, what would you have done? Okay, but first we're going to set up an equation, right? If we're asked to find the zeros, those are the places where f of x equals 0, right? So we would just set this expression equal to 0. Right? And solve. And we can solve that by factoring. We can get magic numbers here, can't we? Right? So we get magic numbers, what here? We get x minus 3 times x minus 2 equals 0. And what do we do then? Yeah, by the zero product property, we know that the product of factors equals 0 only when the factors are 0, right? So that would have given us the zeros, either x equals 3 or x equals 2. We already had this association, didn't we? That the factor x minus 3 goes with the 0, 3. We never thought about it in those terms, but we had it there, didn't we? Turns out that's a two-sided arrow, right? We can go either way with that. for example, I could ask you to, I'm gonna do one before this. What if I wanted you to build a simple polynomial function we'll call it f of x with zeros x equals 2, x equals -3, and x equals 0. What could you do? I want you to think about that. What could I do? Essentially, what we're trying to do here is just turn upside down everything that we've been practicing for a long time. Didn't we normally, I would have given you the polynomial function up until today and said, okay, find the zeros. And you would have set the function equal to 0, factored it, which can be hard, right? Set the factors equal to 0 to get the zeros, right? So we're just going backwards now, right? The second to last step would have been something like this. We would have had f of x equals some product of factors that's equal to 0, right? Okay, so Natalie, then what are the factors going to be? Oh, okay, well, I know what you're thinking. You just got to say it differently. The zeros are 2, -3, and 0. So what would the factors be? And let's take a peek back at the factor theorem again. Whoops, there it is. So k is a 0 if and only if x minus k is the factor, right? So there's the connection. K is the 0, x minus k is the factor that goes with it. So what's the factor that goes with 2? X minus 2, see? What's the factor that goes with x minus 3? X plus 3. What's the factor that goes with x equals 0? X minus 0, which is just x, right? There it is. There's my polynomial function. In this case, they're not asking us to set it equal to 0. They just want to know what is the function with those zeros, right? That's it. All I have to do is multiply it out, which I'm not going to bother doing. But we could expand all that and get the polynomial that way, right? Okay. Could there be more complex ones? Sure. Maybe we could build a polynomial with other zeros too, right? But we don't need to. We want to build a simple one. This is the easiest one, right? Okay. Everybody give me thumbs up, thumbs down, thumbs sideways on that. Okay. Isn't this, I mean, honestly, you got to embrace your inner nerd a little bit here. Isn't this kind of cool stuff? When all this stuff comes together in math like that, it's amazing how it all flows to the same place. And all these concepts wash together and we get this idea that's pretty cool, right? When are we out of here? 53? Okay. So let's take a look real quick. We're not going to finish this, but let's look at this example. They want us to solve this polynomial equation. Now, what's tough about this, this is honestly one that we could do because we could factor that by grouping, couldn't we? Right? Because 25 over 25 is the same as -1 over -1. Pretend we couldn't, though. So pretend we didn't have, that this one wouldn't factor by grouping. We would be stuck otherwise because we don't have any other options at this point, right? But if they give us a 0 of this thing, we can solve this, even if factoring by grouping didn't work. How? So here's our f of x is this polynomial function, right? f of x is this thing right here, right? It's 25 x cubed plus 25 x squared minus x minus 1. What is this part telling us right here? Okay, on the graph it's an x-intercept. Okay, if I know a 0, the factor theorem tells me that zeros always go with factors. What's the factor that goes with that 0? X plus 1/5, yeah. Everybody see that? Everybody see that? So with that, we get the factor x plus 1/5, right? So we know that f of x is equal to that factor times something else, right? And I can even do something else with this. If that's a 0, then by setting this thing equal to 0, we get the answer x is negative 1/5, right? If I multiply both sides by 5 there, does it change the solution? It doesn't, does it? If I multiply each side by 5, look what happens. Then I just end up with 5x plus 1 equals 0. Same solution, right? That's a little more convenient way to write it though, isn't it? No fractions. So I could write this if I want to. I don't have to, but this is a little bit easier, as 5x plus 1, okay? Well, I know that that's a factor of this function. What is the other factor? What's the degree of the other factor going to be? This is a linear polynomial, right? That's cubic. What do I have to multiply a linear polynomial by to get a cubic? Yeah, it's got to be quadratic, doesn't it? So let's just call this q of x, and all we'd have to do is find q of x, right? And then after that, we could find the zeros with the quadratic formula if we wanted to. Okay, we'll pick this up next time. Get your desks real quick. You can tell I get excited about this topic. It's a good one. Yeah. Yes, you betcha. That's no problem, Natalie. I'll see you during advisory. That works.